Hi, I'm Jonas, PhD student in the research group of Dr. Maria Popovic, and I would like to present our work about multi-UAV adaptive path planning using deep reinforcement learning. In our work, we applied deep reinforcement learning for informative path planning, so to plan UAV paths that provides as much information about the environment as possible within a limited time budget. More concretely, we consider a whole team of UAVs where each UAV has to decide on its own where to measure next and also how to behave cooperatively. The UAVs should not just aim for optimizing their own individual amount of information, but should also aim to contribute to much information gathered by the team as a whole. The question on where to measure next has to be made online based on limited information, limited onboard computation power, and close to real time. This was one motivation to use deep reinforcement learning as a learning-based technique to approach the problem, where you have a separate training phase before the actual deployment in the field. We first put some temporal and computational effort into the training phase, but then we basically take the trained network parameter and apply the trained networks in the field, which can be done quite efficiently in constant time. Here, you can see a rough overview over our reinforcement learning. We consider a team of UAVs, in this case a team size of 2, and each UAV takes measurements from the environment throughout the mission. Each UAV holds an own local onboard available low occupancy grid map representation, which is updated based on the incoming measurements. Then there is an actor network, the same for all UAVs, and outputs a policy distribution per UAV, from which then an action is sampled and executed afterwards. During training, we additionally use the critic network. While the actor network is decentralized, means that it only uses locally available information, the critic network is centralized. It has access to a global map representation, which holds information of all measurements taken so far. The critic network is used to approximate the global queue function, so it outputs one queue value per possible action. Special about the reinforcement learning algorithm we used is that it includes a mechanism to deal with the credit assignment problem. The credit assignment problem says that it's hard to estimate each agent's contribution to the overall team performance, and we make use of so-called counterfactual baseline inspired by previous work by Förster and by us transferred to the robotics domain. We evaluated our approach against traditional state-of-the-art planning methods in terms of the map uncertainty and the map correctness, expressed by the entropy metric and the F1 score. Both is only considered for the more interesting parts of the environment, since we want to focus on those parts adaptively. When plotting against the mission time, you can see that our approach leads to a much faster decrease of the environment uncertainty and to a more correct map. For further analysis, I would like to refer to our paper, where we investigate the specific components of our approach in more detail. We evaluate the approach over different team sizes. Here it's a team size of 8 agents, and I want to show you a visual example where the UAVs focus on monitoring the interesting region cooperatively in simulation. The red region is considered as interesting. We also evaluated our approach on real-world data. Here it's for a team size of 4 UAVs. We took surface temperature field data measured by a UAV and consider warm regions, in this case it means higher than 25 degrees, as interesting regions. We took the same approach and the same networks trained in simulation before and applied it to this real-world data, and you can see that it works in the same way. Although we didn't retrain, the regions are mapped in an adaptive and cooperative way, and again, we can show that we outperform the baseline approaches. Thank you for your attention.